Hi, everyone. My name is Mike Nakhimovich. I'm an Android engineer at Dropbox.
And my name is Yiğit Boyar. I work in the Android team at Google.
And today, we're here to talk to you about a library called Store that we've had a delightful time converting from RxJava to Kotlin and coroutines. Anyone that knows us knows that we absolutely love Android. And really, what we love is how easy Android is. Primarily, working with data on Android is easier than it's ever been. We stand on the shoulders of giants. Really not giants, but giant libraries. When we fetch data, we don't have to go to low-level primitives like HTTP URL connection. We can use high-level libraries like Retrofit or Firebase to do our networking for us. Similar for caching. We have solutions from Jetpack like Room, things from Square like SQLite, or even if you're working with files, you can use OKIO. And my favorite, transmitting data in a reactive fashion, we have plenty of options. RxJava started the trend. The Android team gave us live data, and now we have flow coming from Kotlin Coroutines. The thing I get asked a lot is, how do we put it all together? How do we put all these great libraries together into an application? Recently, the Jetpack team has been doing an incredible job giving us guidance of how we should build applications. And this is one I really enjoy, the Guide to App Architecture. I like it because it has this beautiful diagram of how you should architect your Android application. You start with a fragment and activity, which talks to your view model that emits live data. The view model communicates with a repository, and your repository is owning the local source, something like a database, and your remote source, something like a networking client. So let's take a look at what the Android ecosystem gives us to have as implementations for all of these recommendations. We all know fragments and activities. They're in Jetpack. Similar for view models. You don't have to build your own. You can use the Android X, the Jetpack version of it. Local sources, we have Room, which is an ORM that can wrap SQLite, the base implementation for databases. And our remote, even though we don't have a great network client in Android, Square made Retrofit, and we've all kind of settled on that as the de facto network client that we use. And then we have this. They give you a few samples, a few examples of code snippets, but really, they just tell you to figure it out yourself. Thank you for that.
No problem.
So, this is a pattern. This is a problem that is really dear to both of us. It's something that we've both tried to solve on our own. And we thought, why don't we this time try to approach it and solve it together? So before we do that, let's figure out what the problem is that we're trying to solve and what previous solutions or tries of mine, how far they got. The repository pattern was defined by Microsoft's architecture documentations as the class or component that encapsulates the logic that is actually getting your data from what the components that are then using your data. This allows you to centralize the logic for managing your data. You don't have to have parsing logic living in your views or your view models. It can all be in a centralized repository that many UI components use. It removes that burden of having to do logic or having to do fetching within your UI code. And that enables us to build reactive, data-driven UIs with very thin clients that are just reacting to new data as it's flowing through our reactive streams. So this was me many years ago. I looked great. I'll be the first one to say it. And this was me at DroidCon Italy premiering a library called Store that we developed at New York Times. We had a data loading problem at the New York Times where we loaded a lot of data. And one of the table stakes for us was sharing our responses. So let me give you an example. When our app opened up, we had a view pager with many fragments, each for a different news section. And they all needed a config object that came from a config API. Right now, what they did before we had Store was make 4 of the same requests to Retrofit, which will make 4 requests to the backend. Same request, same response, expensive parsing in there, and it's returning a little too much money from your users' wallets. And we kind of wanted to solve that problem, solve that thunder and herd problem. The Times was also one of the first companies to start using RxJava. We loved this declarative way to build our data flows. What we didn't love was the amount of operators that went into building store. We thought it was going to be simple, and it wasn't. So we wanted some amount of abstraction so that we don't have to have every new engineer learning each and every one of these operators, what to do in success cases, how to handle errors, how to do side effects to other components. So we wanted store to be this abstraction that has easy APIs. The way we used store was by building stores that were wrappers around some network client. You would pass it a key, in this case an article ID, and it would return to you a single of whatever the response is. So once you open your store, you can then start making requests to it. You can make a fresh request, passing your key, subscribe to the result, just like any other observable. The only difference between what we were doing with store and what we were doing with just the network clients is that when you fetch the data from the network, we were saving it to a memory cache and then returning it to the user. We were doing this because the other type of request we had was called a GET request. Different verb, same general shape of how you work with it. Here, the GET request, as you can imagine, will just get the data. So if you have it in cache from any GET request or any fresh request, you will be returning that, otherwise falling to the network and then going back up, saving your data to your cache and returning it to the user. And this worked really great for us, so we continued to iterate on it and start building offline stores. Little more complicated builder, but same general pattern. Here, we just pass in a persistor, which knows how to read and write to files is what we were doing, and a naive parser implementation. Once we open the store, our flow starts looking like this. And TLDR, it's just super complicated, and it's, again, not something that I want to do every time I want to build a screen. What store gave us is consistent APIs for all of our requests. We had get, if I just wanted the data and didn't care if it came from cache, and fresh for something like a pull or refresh, where you actually want to get network data. So fast forward 3 years, and store is starting to show some of its age. It was great. It was cutting edge at the time. It used Rx, but it was kind of using Rx singles, where we were returning only single responses from the network. And eventually, users and consumers outside of the Times wanted us to have observable streams as well. We bolted it on by side effecting through streams called published subjects, but it wasn't truly reactive where we can work with observable fetchers or observable databases. So now I'm going to hand it off to Yiğit that's going to introduce what we've been working on.
Thank you. So today, we would like to introduce Store 4, the next generation store library. It is 100% in Kotlin now. We rewrote the whole library. There is no RxJava dependency anymore. We are using coroutines and flow. It supports observable data sources from scratch by default. Either it's your network or your fetcher, so you can use these things like Room or something like a Firebase backend. And most of this is possible thanks to the nice API we get from using Kotlin Coroutines and Flow. But you might ask, why did we go with coroutines? We could obviously implement this using RxJava as well. And of course, the main reason is we are excited. It's just cool. New technology. Honest answer. But there's also a good engineering reason. There's a couple of them. And the main thing for us was this thing called structured concurrency. Actually, if you have seen Roman's talk earlier, I think he stole our slides. Very similar, the same idea. But when you use RxJava, it's a really good library, super cool. And if you subscribe to something, it returns you a disposable, and the function has this annotation called check return value, which kind of warns you, the thing I'm returning you, you need to hold on to it, and you're responsible to dispose it. So it's it warns you to think about the life cycle of that subscription. So it's cool. But in coroutines, this is like the next level, where coroutines makes you think about it from scratch, because the only way to launch a coroutine is a coroutine scope. So without a scope, you can't even start the coroutine. So you need to upfront think about this thing. And very nicely, most of the time when you need a scope, you need it around you. Like if you're an Android developer and you're in an activity, you want to do something in that scope, there's a lifecycle scope. That's the only scope you have available right there. You'll just use it, and it will work, and it's very explicitly scoped to your lifecycle. So we really love that property. This is not the only thing. Another reason is Android X loves coroutine. There's a lot of KTX libraries coming. We're writing Kotlin first things. Room, our persistent solution, supports Flow. Work Manager has a coroutine worker. There's a lot of first-class support. We are even rewriting paging in Kotlin and coroutines. That was the first Kotlin library we have. So there's a lot of investment in Kotlin from the Android and Android X teams. And like Mike and I have this hopeful feature where maybe we don't need to rewrite this code in every single platform all the time, and Kotlin's multi-platform store is quite promising. And if you think about what store does, a repository is almost always about your business logic, so you have very little reason to duplicate it in multiple clients. So, okay, these are the main reasons for like doing store from scratch with Kotlin and coroutines. So let's look at how this API looks like. Again, same thing, we have a builder. You give it a fetcher, and here, all I'm giving it is a suspend function, and this suspend function returns a value. Even here already, like we are taking advantage of Kotlin's Fluent API. The same function could have been returning a flow of values, so if it is an observable backend, in this one, it's just a single. And now you can optionally provide a persister to persist the data. The read function is just a function that returns a flow, and the write function is just a suspend function. Like, these are all like simple, primitive coroutine functions that helps me create this beautiful Fluent API. Last but not least, you can provide a caching strategy or disable it, and then build that store. Once we build that store, in Store 4, there is one main API, and that's called Stream. It's not about get and fresh anymore. It's all about streams. We still have them as convenience, but the main API thinks about the reactive world. You provided a request, and inside this request, you have the key, which key you are trying to get. You have the list of scopes that you want to use, like do you want to use the cache value, do you want to use the disk value, and you can also tell store to refresh the value even if it is available in the cache. And this is another place where Kotlin really helps us, because in Store 3, we used to get this bug where people would use a key that's not really unique, like it doesn't implement equals and hash code properly, and they will complain that it doesn't work. In Kotlin, this is a lot simpler because either it's a simple key that already works, or we will tell people to use a data class, and it still works. This is where Kotlin, again, helps and shines. And one more thing. So this returns you a flow of store responses, another place where we take advantage of Kotlin, because this store response is a sealed class. It might be loading. This is going to tell you where the loading event is coming from, like your network is loading. It might be data, in which case it will have the value. It will, again, tell you where the value is coming from. And it might be an error where we have the exception. One important thing here is that we don't throw the exception. So if your network receives an I/O error, we don't throw it. We wrap it in a data class in this store response and give it to you as an error, which allows your UI to be still observing your database for any other changes while also knowing about the error. OK, so let's go through some use cases and how store works.
So the first use case, what I consider the most common use case of how I work with data, is I want data, and I want updates if that data changes. Like Yiğit said, we'll build a store from an API, passing it a persister, a writer, and then build it. We then are able to call. So he said we had a single API. I like convenience functions and making things easy, so we have a few helper functions. Store.get is a stream that will get us our data from whatever whatever source is the first one that has that data. So we make our store request. As soon as we make the request, store creates a flow for that consumer. Now, looking at our store, we don't really see any data in here. So what we're going to do is make a request to the network. When we start that request, we'll return one of those store responses that are part of our loading store response up through our flow. Eventually, we get the value from the network. Rather than just returning it, we'll save it to our disk, save it to memory, and then flow out. Great. So you had an app. It's just calling store.get and giving you values as you open whatever your activity or fragment is. Now, someone's been using your app for a while. They navigate to different screens and come back to the screen that we were on. There's no state that you really have to maintain within your UI to allow you to get the data for it again. You, again, will just do store.get, same exact request, but now, since we have data in memory and on disk, when we make our flow, we actually return our cached data back out rather than hitting the network. Same code. UI only holds an identifier. We don't have to persist it or serialize it or do anything else besides just holding our identifiers so that we can access that same data again. All right, you've used the app, you've backgrounded it, and now you're going to use all the other delightful apps on your phone. You come back to the app, and now you don't have anything in memory when you get that same request of your app coming back up. So let's say there was process death in between you using the app and then coming back to that same screen. Now, when you come back in, you have data on disk. You make your store request. We fill memory again so that every request past this one will be quick, and return it from disk. That was the simple, most common case, but a lot of apps actually work similar to what Gmail does, where when you open Gmail, you see your old messages, and then you actually want to refresh and get your new messages as well. So we have some data that was already in memory and on disk. And here, rather than calling store.get with refresh false, I'm calling it with refresh true. And this is where we shine that now we are flows, so we can return multiple values. We'll first return whatever values, if we have them in our cache. We'll then signal that we're going to be loading from the network, make our network request. Oh, we got a new value, 2 instead of 1. So let's update disk, update memory, and return 2. Similar, we can work with a stream, skipping that cache. So when we get that request, we make the flow. We're not going to get values from disk since we did a store.fresh. That's the only difference. I would think this is something like a pull to refresh would have this rather than just a get call. We'll return the loading and go to the network. So fresh makes it always seem as though you do not have something on disk from the perspective of the UI. And that's really the only directive that you really have to think about of, am I getting data or am I getting fresh data? The more complicated stuff that we were unable to do with Store 3 when we were working with just singles is what if we had observable sources? Like now room exists, and we could actually listen for a flow coming out of room. We'll think about this example as a to-do list, where you both have data locally and from network. When we make our request, because we're making a store get request, and we already have data locally, we're going to return from that store whatever that data is, just like the other ones. Now, the only difference here is if our database actually gets a new value that gets emitted from whatever that reader flow was, we will, in fact, emit that to the user as well. So you could actually work with both observable databases and observable networks. Let's say one's a WebSocket and the other one is Room, and both of those updates will flow through your store back up to your user. What I love about this is how easy this case is. It's every bit as easy as the simple case is. You're really only changing a verb or some directive, and you're able to interface with your store in the same way that you do with really basic APIs. Now, I say this is simple and easy because I like being a consumer of a library, but there's actually a lot of complexity hidden under here to make source of truth work, and Yiğit's going to do a deep dive on it.
So source of truth is one of the concepts that's like very, very easy to get wrong. I'm going to show a use case here. I'm pretty confident that most of you can relate to this. So I have an application here, let's say it's like Dropbox or Google Drive, that lists the folders I have. I hit the plus button, add a new folder for KotlinConf, hit save, it goes back. I'm seeing the loading spinner. I'm not seeing the KotlinConf there, none of it. And only after it finishes loading, I see KotlinConf. This is a horrible user experience. I just saved something on my phone. I have no idea where that folder go. Did it even save? I cannot use it. You don't want to put your users into this state. So what's happening there? What's the problem? We have that first screen that lists all of our folders, and that makes a network request, gets that list, and displays. And then you go to the add screen, which makes another network request, adds the new folder, is done. You go back to the previous screen, makes another network request, gets the updated data, and if everything works, like you are not in a metro or anything, it shows the data. So the problem here is that you are missing a reliable source of truth that's locally accessible. So we want to put this. It's like usually a database, might even be the file, like something you can modify locally and then synchronize to your backend asynchronously. Meanwhile, your UI can be snappy because it's just loading local data. You don't need to rely on network. So when we're trying to design Store 4, one of the questions is, should we make this store? Like, should we make store a library which handles all of the persistence of your data plus fetching it and just like a one-stop solution? And really, in terms of API, it boils down to just one single API difference. In Store 3, we had this API with the persisters where you could put a value or get a value. Instead, what we wanted to do in Store 4 was this. We wanted the local persistence to be able to return a flow. That means it can actually update itself without going through Store. Obviously, the advantage of the first implementation we had in Store 3 was it was very easy for Store. It only had to track what it knows. It never got invalidated by other things. So it was an easy implementation. The flow of code was always one way. But the problem with that solution is that it forces you to rely on Store for everything. So if you want to start using Store, you have to move everything to Store, or it will be inconsistent with the rest of your application. And if you want to do a partial migration, every time you change your code, like you have something that updates the database, you have to inform Store. Like, for example, if in my application I had some code that ran a simple SQL query to update some records, you cannot do that anymore if Store doesn't support source of truth. You also need to tell Store to invalidate some data. And this is just ugly. This is bad developer experience. We said we don't want this. So what we ended up doing, and also there is one more thing, where when Mike first designed Store for 3-4 years ago, it was a different world. There was no public room, the observable databases wasn't a common thing. So it was a different world. Today, we have Room, SQL Write, RAM. These are all observable data sources. They already do the hard work. Why not just build on top of them? So if you go back to the previous question, we said, no, Store shouldn't be your source of truth. Store should just work with your source of truth. You can just think that as your database. That's the most common case. It should work as a mediator between your local storage and network and whatever else you have. And if you look back to if you remember the architecture diagram Mike showed before, this exactly looks like a repository. So kind of, yes, we are in the right space. It looks the same. So when we go with this model, that means it fits the current architecture recommendation. It should be easy for people to migrate to start using Store. It allows out-of-bands updates. It's your source of truth. It's your data. You can change it however you want. Store will catch up. It simplifies user code. You don't need to think about managing Store, which enables partial migrations. But it's easy to say, nice graphics, Mike, but it's very not easy to implement. So we showed before, every Store response comes with an origin. We want to tell you where this data is coming from so you can update your UI properly. Because let's say you want to get a fresh, you are just getting requests, you want to know if it came from the network or if it came from the local storage to properly update your UI. So in theory, how this works is when we get data from your database, it comes to Store, and it just sends it to the downstream flow. We get value from your network. It comes to Store. We cannot send it to downstream now, because this will invalidate the source of truth. What if you have a trigger in your database that will update the fields when you insert the record? We cannot send the value to the user without giving it to your disk. because it's the single source of truth. That's the whole point behind it. So what we do instead is, when the data comes from the network, we first write it to your database. We know it's observable, it's the API. It will send us an update, but we know it's the update we just gave it, so we change the origin, back the network, and send it to downstream. It can even change the type, which happens very frequently, right? The class you fetch the object from your API endpoint is usually not the same class you use to persist it. So this allows you to control all of that. Now, that wasn't very trivial, actually, when we were writing. And this is another place, like maybe us learning coroutines properly. But the first implementation we had was something like this. Basically, put this item into the store, and then mark the next item as if it's coming from the fetcher, so we can change the origin. But when you do this, this is a suspend function. Actually, we wrote this. It was working fine in practice. But when we tried to write tests, it broke. The problem was this. When you put an item, we are suspended. So we have zero control over the implementation of that source of truth or when it will inform us. It might actually inform the downstream flow while we are writing the item, which means now we don't know that this actually came from the network. We think it comes from the disk. So we have to change this. And what we ended up doing is we wrote something that could suspend the flow. So we'll like stop all the flows that's observing that key. Then update the value. Mark the next one as coming from the network, like a flag. And then restart those flows, because when we restart them, we know we're going to get a new value. And that's the value we have written. And now we can comfortably change it. So Mike showed a very simple API. This is what store allowed us. Like, this gets fairly complicated. It was very easy for us to write this thing. And the public API doesn't even know about this. And now we send it downstream. Errors are a little bit different because your data source doesn't usually care about the errors. We just send them down as they are. So there's a lot of custom code, but the simple API.
So that was great. I was really excited once we got that working because there was a feature that I've always wanted to be in store, and we were unable to do it before. Got a little help from this guy. Big thanks. But we also had features in store that worked really well and worked really well in RxJava. And one of them was that stores are actually concurrent. And there's a big difference between something being synchronous and concurrent. By concurrent, I mean any number of requests should not slow down how one response will come from the server and propagate it to them. We don't want to do them one after the other. So let's look at our store.get example again. And we're collecting it in the UI. So one fragment makes a store request for a path and saying we want cache data. We generate a flow. But then we get a second request for the same key. We get a third request for the same key. And now we have 3 active flows that all want the same data. Because the data doesn't exist in memory or in our source of truth, we'll create a loading store response and then multicast it through all 3 flows. Similar, we'll only make one request to our backend, get one response, save it to our source of truth, save it to our memory, and then multicast it to any flows that wanted that data. And I absolutely love this because I write a lot of bad code, and this makes my bad code not so bad because it'll still get throttled within the store. And this actually took us on a really far adventure of how sharing works in Flow.
Okay. So when we converted Flow to use store to use coroutines, that was a pretty straightforward conversion because it was all single. And every time we've shared something in the RxJava version, we'll just put a share, and it works. So we convert this to Kotlin. We have the flow. We put a share. It doesn't work. Because there's no share. It just doesn't exist. Which is fine. It's a new library. Like, we know what we are getting into. Like, fine. Mike said he'll write it. I mean, he knows RxJava. And after like 2 weeks, he's like, nope, let's go back to RxJava. It just doesn't work. He's like, we can't write it. I'm like, don't worry, I will do it. I couldn't.
He's a pro, is why I was very happy, yeah.
So we decided that maybe we should learn how Flow works. Anyways, the thing we were missing was this property of flow, very nicely documented. It's called context preservation. That's a new concept we didn't initially understand. Let's look at an example where it might make sense. So imagine we wrote this magical share operator on a flow. And now we have one collection using as like scope, another collection using another scope. Each of them has their own context. So now, where do we collect this upstream scope? If we pick one of the scopes, what if it gets canceled? Do we cancel the other one as well because they happen to be sharing? Like, there is no way you can move a job from one coroutine context into another. There's no transfer operator or anything like that. So this is like fundamentally hard for us. And then we came to the conclusion that if you want to share something, you got to tell us where to share. So you need a scope to say that. So we need the actual upstream scope that will do the consumption of the upstream flow. And the other flows will be just getting that value in their own context. So then we start writing this multicasting class. And this is all private API. You don't see any of it, but we found it fairly interesting to implement. So I want to go deep on that a little bit. So we have these three classes. The multicaster is just the entry point. It gets your upstream flow, gives you a downstream flow in return. This channel manager is a store actor. Like I really like store actors. They're so beautiful, handles your concurrency in a very sweet way. So there's an actor that does all this complicated logic, and then producer is the one that wraps the upstream flow to talk to this channel manager. So let's see what happens when you run it. When you get a downstream flow from the multicaster, it's just a flow, nothing happens. But then when that flow starts collecting, it starts talking to this channel manager. So let's look at that relationship. This downstream flow creates an unlimited channel for itself. Keep in mind, when you want to start thinking about going between contexts, you need to have a channel. Flow doesn't do that. Flow is always in the same context by itself. So this downstream flow will create a channel for itself and send it to the channel manager. Even though this is an arrow, this is not a function call. It's just a message to the inbox of that actor. And this makes concurrency very easy. When we receive this message, channel manager says, OK, I have a downstream channel. There's no producers. Let me start collecting on the given scope. So we had a scope. When this producer eventually gets a value from the shared flow, so one is the value, and it adds an ACK into that value. So this ACK is so that is a simple completable deferred. I don't know what's a Java for completable deferred.
A Boolean?
Countdown leg? Whatever. So it's like a lock. So it attaches it to this and then sends it to the channel manager and waits for that acknowledgement. This is so that we can control the back pressure. We don't need to consume the upstream if none of the downstream actually delivered the message. Something you need to be careful when you start using channels because they are hot. So the channel manager will send it to all of the downstream flows. And then eventually one of them will, when they get it, they emit it to their own downstream. They will acknowledge this message, which will unblock the producer. So it can get a new value. So we get another downstream flow. Now, if it does the same thing, it creates a channel for itself, sends a message to add it to the list. And if caching was enabled, we will give it the previous value. In this case, the caching is not. So it'll stay there. A producer gives us a new value. The same thing, it gets an ACK. Channel manager sends this to both of the channels that it has. It's the same ACK. So if any of them happens to consume this new value, because they might be suspended, but if they can consume, the first one will unlock the producer to get more values. We can get a third one at this stage. It also adds the stuff to the list. But after it came, the producer decides that it doesn't have any more values. Now that's finished. We want to finish the downstream. We finished the first two. We just canceled those channels. But this third one was just an unlucky one. It happened to arrive right before the upstream flow finished. So you don't want to just close it without any values because we know there were values. And also think about it, this is for store. This is mostly for a network call. So like you would make it again. So what we do is exactly that. We get a new producer just for that one. We start running that producer. It produces values. The same thing continues. Now, if we happen to get a fourth downstream flow at this point, but then after some time, the upstream flow just crashes. It throws an error for whatever reason. That message arrives to the channel manager, knowing that the upstream flow died. This time, we just cancel both of the downstream channels with that error. Even though the fourth flow never received a value, an error is as good as a value from our perspective, so we just cancel it with that given error.
Great explanation. So we mentioned that we had store was a library that already existed. We started converting it. We added new features to it. We weren't sure if new features were buggy or not. And we also weren't sure if we understand what flow does and whether it's doing what we knew observables and singles do in RxJava. So we needed to migrate our tests as well. First thing, we just converted the test to Kotlin so that we can start using new language features. And next, we kind of looked at our test structure. We had a couple of hundred tests, and they mostly fell out of bug reports that users had over the years of this race condition or that race condition and how to store deal with it. So we took this configure store function and instead made common builders that can build both a store 3 and a store 4, our new implementation. We then did bindings back to store 3 APIs, because that's what tests we're running under, and then leveraged JUnit's parameterized testing, which allows you to pass in a parameter. Our parameter was which one of these builders do you want to use, and it actually ran through our test suite using old store code and new store code. And this was great for us, both for adding integrity and for realizing that things like share, our first attempt, our second attempt, our third attempt, all just did not do what we expect. It seemed like it worked. Like he said, it worked when we put it in an app, but it didn't work when we ran our test suite. So we were really happy that we were able to leverage a project that already exists and leverage all the tests and all that knowledge that we had from community to make sure that we're starting over with a clean rewrite, but we're not starting over with what features and what validations we have in this project. And this led us to a nice piece of kit called TestCoroutine Scope.
So I want to add some testing slides because there was another testing code you didn't go. This is a backup. So the very first time we did this migration to coroutines and the test, in the test we just did run blocking everywhere, and we made all of them pass. And then TestCoroutine Scope came around. TestCoroutine Scope is just a coroutine scope for testing. And we tried to move to TestCoroutine Scope, and out of test didn't pass anymore. Which, they were passing, they're not passing. Some of them are our bugs, some of them are their bugs. But it has two really interesting properties we want to share. First of all, TestCoroutine Scope is very good at catching unnecessary work, like work leaks, the work you're doing unnecessarily. And the second thing is it allows you to create very interesting testing scenarios. So let's go through how this happens. I have a flow here. It's a channel flow, and inside I'm launching on a scope, sending a value, waiting for a second, and sending another value. There's nothing interesting here. If I observe this in my application, within a second, I'm going to get 2 values. So let's write a test. We create this TestCoroutine Scope. In the test, you use this test scope.run blocking. We just want to assert that if we collect 2 values from that flow, they're going to be 1 and 2. It's fairly simple. You hit run, and this test fails. If you run it on your phone, it works. You run here, it fails. And it's also a rather cryptic error. It says the job hasn't completed yet. What does that even mean? What it tries to tell you is that it executed everything it should execute, and there's some coroutine that's still running somewhere. It should have been finished. It didn't come back. There's some inconsistency, and it doesn't know why. If we go back to the example, what was happening in this one, and we had a lot of these. It was a red herring to find why they're happening, but it's always our bugs. In this sample, I was just launching on another scope. Even though this code works, there's a problem here, because if you stop collecting from that flow, this myScope.launch, that section will not be canceled. It has no idea that the other one is canceled. It will only ever cancel when it tries to send a value to that channel, which is canceled, and it will realize, oh, OK, let me cancel. So we had a bunch of leak work here and there in store. It will just keep running for no reason. But when we were testing with run blocking, we didn't catch any of these, because it could just keep running. But when we tried to move to TestCoroutine Scope, suddenly all of these problems showed up. So easy fix here. We just get rid of that scope launch. And now we run the test. It will pass. I will also pass in a duration like 100 milliseconds or so. So we have a test that has a 1-second delay in it. And the test passes less than 100 milliseconds. It doesn't make much sense. So what's happening here is that the time is fake. There is no real time in TestCoroutine Scope. It's a controlled time. And the fact that it's a controlled time is actually allows us to create very interesting scenarios. That's the second part of why we like this. So imagine you have some test subject that receives like 2 flows. And you send it to them, and you want to create different scenarios of different values coming from these flows. So we'll just say 1 flow, another flow, and then give them to the subject as a merge. This test, this code is predictable. I know the values from the first one will go first, and the values from the second one will go next. If I want to change the order, I can just say delay 1 on each. I'll make the second ones come first, and the first one comes later. And I can even go into more detail to say, OK, I want 2 values from the first one, and then 1 value from the other one, and then more values from the other one. Just keep in mind that this delay is fake. It doesn't really delay for that. It just reorders the execution. And imagine writing a library like store. You have a fetcher, you have a disk. They're all coming in, like they're running in parallel. They're independent of each other. They might send values in different orders. They may crash in different orders. So we wanted to create test cases for all of these. And heavily using delays, we were able to cover a lot of different test cases and make sure store handles it. So I know what I did. I just recommended using delay or sleep for your tests.
We expect to see that on Android subreddit within the next 5 minutes.
Yeah. I'm behind it. Because like, this is, first of all, this is not real time. It doesn't slow down your tests. It is predictable. And this is very useful to create very edgy race conditions that you cannot easily create otherwise. So I don't know. I really enjoyed doing this, and it might be useful if you're writing a library that's also highly parallel, like store. What's next?
So this started as a library, kind of like a pipe dream that I had to try to learn a little RxJava. When I worked at New York Times, I was delighted that I was able to convince them to share it with the world. Since that time, we've gotten over 30 contributors externally, and I actually moved on from New York Times 2 years ago. They've been great partners continuing this project and making sure it's up to date and making sure that it's still working as well as I always wanted it to. But today, we want to announce Store 4. And what we want to announce is that Store 4 is going to be moving to Dropbox. We're going to do active development on the Kotlin version of Store within the Dropbox repo. And we want to open this up as a call for action. It's already a community project. This is already something that we're getting community contributions from.
The community.
The community, yeah. And you know, we're releasing this as 4.0 alpha right now. We really want to get feedback from everyone of, does this API fit your use cases? This was a tiny library that I wrote just to use at New York Times for the particular case that we had. But it's gotten to something much larger than that. And what I hope that this will become is the definitive implementation of a repository pattern on Android, and we can't do that without all of your help. So once again, I'm Mike Nakhimovich.
I'm Yiğit Boyar, and don't forget to vote. Thank you.
Thank you.